Why does the universe always manage to find the most efficient path of evolution amid chaos? The secret is actually hidden in a math problem from hundreds of years ago, from a tiny steel ball to all the planets. It seems that all motion follows the same rule. In the next 20 minutes or so, I will take you to uncover this profound principle, because all of this points to an incredible truth. Asterisk, that is, the universe itself is optimized. As early as 1696, Johann Bernoulli posed a question that would later become one of the greatest mathematical challenges in history. The question is simple. Given 2 points at different heights, and assuming no friction, if a bead travels from one point to the other, what is the fastest path? It is not the shortest path, but the fastest one. Most people would instinctively say it is a straight line. After all, the shortest distance between 2 points is always a straight line. That is true in everyday life. But under the influence of gravity, the rules of motion are different. A straight path does not make full use of acceleration. It starts off too slowly and does not build up enough speed early on. Bernoulli realized this. He was not just asking a random question. He suspected that nature follows some hidden principle of efficiency. He called this the brachistochrone problem, also known as the problem of the shortest curve. He believed the answer to this problem would reveal some fundamental laws about the motion of objects, not just on Earth, but anywhere gravity exists. So he issued a challenge. He sent the problem to the greatest mathematicians of the time, including Isaac Newton and Gottfried Leibniz, the co-founders of calculus. This was more than just a friendly puzzle. It was a test of pure mathematical genius, a way to see who could truly understand the hidden rules of nature. And he did not give them unlimited time. He set a 6-month deadline. If they were as smart as people said, they would find the answer before then. If they could not, maybe they were not as great as everyone thought. It was a bold move. Bernoulli was famous, but not as famous as Newton yet. Newton was the scientific superstar of that era. He completely changed physics, the man who invented calculus and basically rewrote humanity's understanding of the universe. Bernoulli respected him. But this challenge was almost like poking a sleeping beast, and when Newton finally received this problem, his response would become legendary. Before we get into that, let us talk about why this problem was so difficult. The key issue is, this is not just a geometry problem, it is an optimization problem. You are not just looking for a shape, you are looking for a path that minimizes time. That is much harder than just dealing with simple geometry. Imagine this. If you start off with a steep slope right away, you will accelerate quickly. That is good. But if the path is too steep, you might not have enough horizontal movement. The speed does not reach the target. On the other hand, if the path is too gentle, you won't build up enough speed at the start. The perfect solution must balance these two effects. On one hand, you need to accelerate early, and on the other, you have to keep moving effectively toward the goal. At the time, there was no simple way to solve this problem. Mathematicians did not use computers or software like we do today to test different curves. They could only rely on pure mathematical reasoning, and the tools they had at the time, basic calculus and geometry, were not enough to solve this problem directly. But Bernoulli believed there was an answer. He had an intuition. He believed that this curve was not random, but rather a fundamental law of nature, closely linked to the way objects move freely. He just needed to find someone smart enough to solve this puzzle. As it turned out, one person did not even need 6 months. He took one look at the problem and solved it overnight. That person was Isaac Newton. Legend has it that Newton was pure mathematical firepower. He did not even bother to write back to Bernoulli with an explanation. He simply provided the correct answer. When Bernoulli saw the answer, he immediately recognized the reasoning, and he is said to have remarked, "I recognize the lion by his paw." This was an acknowledgement of Newton's undeniable mathematical genius, even though the solution was unsigned. So what is the answer? Under the influence of gravity, the fastest path is not a straight line. It is a special curve called a cycloid. It is the shape traced by a point on the edge of a rolling wheel. If you have ever watched a bicycle wheel spin and followed a point on the tire, you have seen a cycloid in action. So why is this curve so special? It all has to do with acceleration. When an object moves under the influence of gravity, its speed increases as the falling time increases. A cycloid takes advantage of a steep initial descent to quickly build up speed, much faster than a straight path. However, the cycloid does not keep going downward all the way. Instead, after accelerating, it gradually flattens out, allows the object to maintain this speed as it moves toward the target. In contrast, a straight path is inefficient. It does not let gravity play enough of a role early on. As a result, The object moves too slowly at first. It can't make up for this shortfall. Meanwhile, a steeper descent, almost a vertical free fall. Too much movement is wasted in the wrong direction. Extra time is needed to correct the course, but the cycloid is the perfect balance point. It accelerates quickly and efficiently maintains that speed all the way to the end. This is a profound discovery. It is not just a mathematical trick. It is a fundamental insight into how motion works. The path that minimizes time is not random. It follows the same rules that nature itself seems to follow. The cycloid is the path that gravity wants to take. To prove that this is not just a theoretical result, Bernoulli and other mathematicians later built a physical model of this problem, using ramps of different curve shapes and letting objects slide down them. Every time, the cycloid curve won the race. What is even more interesting is, it turns out that this curve appears far beyond just rolling objects. It shows up in the path of light, in space travel, and even in quantum physics. Because, fundamentally, it is about more than just rolling marbles. It is about how nature optimizes motion. But before we dive deeper, we need to talk about something more profound, the principle of least action. This principle connects the curve to the fundamental laws of the universe. So why is this curve so important? At first glance, the cycloid curve might seem like just a mathematical trick, a clever way to solve the rolling bead problem. But it is much more than that. What makes this curve so special is that it follows a profound rule about how nature works. In fact, this problem is very similar to another one. Fermat's principle. When light travels from one point to another, does it always take the shortest path? You might think so, but that is actually not the case. When light passes through different media, such as air and water, it refracts. It does not just travel in a straight line, but instead follows the path that minimizes total time. This is Fermat's principle, which is very similar to the brachistochrone problem. Fermat's principle is a fundamental concept in optics. It states that light always travels along the path that minimizes time. When light encounters the boundary between two media with different refractive indices, it refracts, adjusts its trajectory to maintain efficiency. Surprisingly, this principle echoes the brachistochrone problem. When a bead rolls under the force of gravity, it does not move in a straight line. Instead, it follows a cycloid path, reaching its destination in the shortest possible time. Both phenomena reflect nature's inherent tendency toward optimization. It is not just about optimizing distance. It is also about optimizing time and efficiency. In fact, the entire universe seems to favor paths that minimize something. Whether it is time, energy, or other physical quantities, the principle of least action tells us that the motion of things is not random. They move in the most efficient way, according to the laws of physics. The path of the cycloid demonstrates how nature tends to conserve energy while getting the job done. The bead uses gravitational potential energy in an optimal way, minimizing the time required. This shows how nature achieves results in the least amount of time, with minimal energy expenditure. Nature often chooses those paths or forms that are not necessarily the simplest geometrically, but are optimized for the dynamics involved. Similarly, engineers often imitate nature's solutions in their designs. Cycloidal curves can be seen in many applications, such as roller coaster tracks, and even in the design of optical lenses, where the path of light is also optimized for greater efficiency. In chaotic systems, patterns like fractals and attractors emerge, revealing a deeper order hidden within complexity. This order is a direct result of underlying optimization principles. For example, the fractal structure of coastlines or the branching patterns of trees can be seen as nature optimizing energy dissipation or resource allocation. This is consistent with the principle of least action. In every field, nature shows a preference for solutions that balance effort and outcome. It tells us that efficiency is a fundamental principle deeply rooted in the nature of reality. Newton's laws of motion can actually be restated using this principle. We no longer describe how forces push objects, but instead describe motion by saying that objects follow a path that minimizes something called action, which is a quantity. Action is a combination of energy and time. The cycloid curve is an example of this principle. It is the path that minimizes travel time under gravity. This idea is not just a clever way to solve the rolling bead problem. It has become one of the foundations of modern physics. It led to the development of Lagrangian and Hamiltonian mechanics. These approaches are now used in everything from classical physics to quantum mechanics. This principle appears in astronomy, engineering, and computer science, even economics. Any system involving optimization, whether it is designing efficient transportation routes, predicting the motion of planets, or training artificial intelligence, can be understood through variations of this principle. When Bernoulli posed the challenge in 1696, he was not just solving a math problem. He inadvertently touched upon the deepest laws of nature. These laws apply to everything from the motion of planets to the strange behavior of quantum particles. Yet this raises another question. If nature is so adept at optimizing motion, where else can we see this principle applied in real life? The answer might surprise you. Because the cycloid curve is not just a mathematical curiosity, it appears in some of the most unexpected places. From roller coasters to space travel, if you have ever ridden a roller coaster, you have already experienced a cycloid curve, without even realizing it. The most thrilling roller coasters do not just drop straight down, they start with a steep descent, and then gradually level out. That is because dropping straight down is not the fastest way along the track. By imitating the cycloid curve, roller coasters can accelerate efficiently, while ensuring a smooth and fast ride. Engineers use this principle to design roller coasters, to maximize acceleration at the beginning, so the experience feels fast and thrilling. When spacecraft navigate in space, they do not just travel in a straight line from point to point B. Space travel is not just about covering distance, but about optimizing the use of time and fuel. Space agencies propel spacecraft using gravity assists. This is a carefully planned maneuver that allows a spacecraft to fly by a planet and gain speed with minimal energy consumption. This method is similar to a cycloid curve. It shows us that the fastest path is not always the most direct. Similarly, when launching a rocket, the goal is to reach escape velocity using the least amount of fuel. The initial ascent path is steep, so that speed can be gained quickly, while also minimizing the time spent entering the lower atmosphere. It is just like a cycloid curve. At first, it is steep to accelerate quickly, then it transitions to a more efficient path. Missions like Voyager and Cassini have made use of this principle. They use planetary gravity to accelerate efficiently. Just like a bead on a cycloid curve moves faster than one on a straight slope, it is like reaching the bottom faster. Spacecraft follow curved, energy-efficient trajectories instead of forcing their way straight through. This allows for faster and more efficient travel, although real-world rocket trajectories, due to atmospheric drag, gravitational changes, and propulsion limitations, do not exactly follow a cycloid curve. The fundamental idea behind the cycloid, finding the most efficient path under given constraints, still applies. It is not just objects that follow these optimized paths, information does too. When you load a web page, your data does not travel in a straight line from the server to your device. Instead, the internet finds the fastest route, taking into account factors like traffic congestion and server response time. To minimize latency, just like the cycloid reveals the fastest path for an object moving under gravity, routing algorithms determine the most efficient way for data to travel across the internet. If one route is congested, the data will choose another path, just like a traveler avoiding a traffic jam. Latency is the time it takes for information to move from one point to another. It is also minimized in the same way nature seeks the path of fastest descent. Even server load plays a role. Data flows through less busy servers, thereby reducing response time, just as physical systems naturally optimize motion to minimize resistance. The same mathematical principles that govern the Brachistochrone problem, finding the most efficient path under given constraints, also play a role in internet routing. Whether it is a moving object, or a spacecraft navigating through space, or the data flowing through networks, both nature and technology follow the logic of efficiency. This kind of optimization is equally crucial in finance. High-frequency trading firms use similar mathematical methods to minimize the time required to execute trades as much as possible. Sometimes, they even optimize down to the microsecond level. Although the cycloid curve is directly applied to physical motion, its optimization principles also resonate with evolutionary biology. Evolution often favors energy-saving solutions. Whether it is the branching of human blood vessels or the way animals move. When animals migrate, they do not always take the shortest path. They choose the path that minimizes energy consumption over long distances. This often results in curves similar to cycloids. Similarly, species adapt to traits that optimize survival and efficiency, just as the cycloid curve optimizes travel time under gravity. For example, the structure of bones or the shape of bird wings have been optimized to achieve the best balance of strength, weight, and aerodynamics. Even human decision-making processes follow the principle of optimization. When we solve problems or plan routes, our brains subconsciously look for the most efficient way to complete a task. That is why when you walk through a pitch, you might naturally choose a winding path instead of a straight line, because this minimizes your effort over the terrain. Similarly, Biological systems adjust their behavior or structure through feedback loops to achieve optimal performance. For example, the body's homeostatic mechanisms ensure that conditions like temperature or glucose levels remain within a narrow range, thus optimizing the processes of life. What initially seemed like a simple question, how to make a marble roll down the fastest, ultimately became a profound principle that appears across many fields. The cycloid curve is not just about motion, it is about efficiency. It is a concept that appears in physics, engineering, and biology, even the mathematical fingerprints in human behavior, but perhaps its most peculiar appearance is in quantum physics. There, the structure of reality also seems to choose the most efficient path. This leads us into an even more perplexing realm. How does the cycloid curve connect to the quantum world? At first glance, a rolling bead and a quantum particle do not seem to have much in common. A predictable pattern that follows classical mechanics moves along a curve under the influence of gravity. The other exists in a strange world of probability waves, superposition, and uncertainty. But one lesson physics teaches us is that patterns in nature often repeat across different scales, the same principle that determines the fastest path for a bead to roll. The cycloid curve, it also plays a fundamental role in quantum mechanics. It all comes down to a simple yet profound idea. Nature always seems to choose the most efficient path. In classical mechanics, if you throw a ball, its path is predictable. It follows a parabola determined by Newton's laws. But in quantum mechanics, things get weird. According to Richard Feynman's path integral formulation, a quantum particle does not take just one path. Instead, it simultaneously takes all possible paths from point A to point B. This means that if you send an electron from one place to another, it will theoretically explore every possible trajectory, including some completely absurd paths, like passing through outer space or bouncing off distant galaxies. But not all of these paths contribute equally. Only those paths that produce constructive interference, that is, the paths favored by nature, are precisely those that minimize a quantity called action. Is not that the principle behind the cycloid curve? Just as the cycloid is the mathematically optimal path that minimizes time under gravity, quantum particles tend to choose paths that minimize action. In other words, the same mathematical principle that governs a bead rolling downhill also governs the most fundamental laws of the real world, especially at the smallest scales. In quantum mechanics, there is a topic called the quantum brachistochrone problem. It explores the fastest way to transform one quantum state into another. Just like in classical physics, the fastest transition between two states is not always the simplest or most direct. Quantum systems evolve over time according to the Schrödinger equation. Researchers have found that the principles behind cycloid curves can be applied to quantum computing, quantum gate operations, and even the time evolution of particles. This has real-world significance. If you are designing a quantum computer, you want it to perform operations as quickly as possible, minimizing errors caused by environmental noise. Understanding the fastest way for a quantum state to transition. This is crucial for making quantum computing truly viable. And once again, the mathematical principles of the cycloid curve come into play. Whether in classical systems or quantum systems, they all exhibit a profound tendency toward efficiency, whether it is minimizing time, energy, or action. This suggests that nature itself is governed by an intrinsic driving force in pursuit of optimal solutions. In the quantum world, systems evolve along paths that optimize specific constraints. This reveals a profound unity within the laws of physics. The pursuit of efficiency transcends scale. It connects the macroscopic and microscopic worlds. What does this mean? It means that the universe wastes neither time nor energy. Whether at large or small scales, whether it is a bead rolling down a ramp, or light refracting through glass, whether it is planets moving along curved paths, or electrons jumping between quantum states, their motion always follows the optimal path. The brachistochrone problem appears in such a wide range of physical fields that it suggests optimization is a fundamental feature of reality itself. The brachistochrone problem is not just a curiosity from the 17th century. It was an early glimpse into a profound fundamental principle that governs everything from classical mechanics to quantum theory. But there is another question worth considering. If the universe is built on efficiency and optimization, what does that mean for us? Everything we experience, is it all influenced by these invisible principles of least action? Why does the universe favor efficiency? Think about how rivers carve their paths. Water does not flow in a straight line. It always finds the most efficient downhill route. Often, it forms curved, optimized paths. Light passing through glass, the orbits of planets, even the way the human body moves. They all follow the same principles. Evolution itself is an optimization process. Biological systems adapt to their environment to maximize survival and minimize unnecessary effort. But why is that? Why does nature always find the best way to do things? One possible answer is that the laws of physics naturally select for efficiency. The motion of objects is not random. They follow specific rules. Minimizing waste, in a certain sense. The principle of least action and the cyclic curve reveal a profound truth. The universe is not just a chaotic collection of random motions. It is an organized system that follows deeply embedded mathematical principles. Nature's pursuit of optimization does not come conscious thought or decision-making. On the contrary, only those systems that operate efficiently can persist and replicate and remain stable under the constraints of the universe. As time goes by, this leads to a process of natural selection that favors not just what is functional, but what is inherently optimized in terms of processes, behaviors, and structures adapted to their environment. Efficiency is not a coincidence, but rather a part of the very structure of reality. This principle applies not only to physics, but also to human behavior. Efficiency even plays a role in art and music. The best designs, melodies, and structures often find a balance between complexity and simplicity. It is an optimized form of expression that just feels right. The cycloid curve is just one example of a deeper pattern in nature. We see it everywhere. Light follows the fastest path, the principle of least time. Objects move along paths that minimize action, Lagrangian mechanics. Quantum particles take all possible paths, but in the end, the paths that are followed are those that obey the principle of optimization. Feynman path integrals. Evolution favors energy-efficient survival strategies. What started as a simple physics problem, proposed in the 17th century, ended up becoming a fundamental law of existence. The universe is optimized. It always finds the optimal path, whether we realize it or not. We are also part of this process. Now let us go back to the original question. If you want to slide from point A to point B, what is the fastest path? The answer is not a straight line. It is something much more elegant. It reveals the hidden mathematics that shape our world. Once you see it clearly, you will start to notice it everywhere.